we've come a long way from manifolds over Lie groups, Lie algebras and back, and we're now fully prepared to come to the at least technical climax of this course, and that's our chapter 5. That's principal fiber bundles. So what's a principal fiber bundle and why is it so important a notion? Well, because this is going to require some technical developments and some rather technical developments at some points, it's maybe good to know what this is all about. So let's start by claiming or stating that very roughly speaking, and to make this precise is, of course, exactly the point of the technical developments. But very roughly speaking, a principal fiber bundle is a bundle whose fiber is a Lie group. So this is why Lie groups are also so important, because they provide the fibers of fiber bundles. Okay, so that is what it very roughly is. But why is this important? This is so immensely important, or principal fiber bundles are so immensely important because they allow to understand any fiber bundle with a fiber F. So that's a different guy. Any fiber bundle with a fiber F on which the Lie algebra G acts in a particular way. Well, we could say acts. Well, it's always in a particular way, but it acts. Okay, and these fiber bundles on which G acts and that are associated with this principal bundle are called associate bundles. These are called associated bundles. And in physics, fiber bundles are really ubiquitous. They appear everywhere. To just mention a few examples, for instance, in general relativity, they appear, and the fiber is given by the SO13 Lorentz group, or if you consider spinors, by SL2C, which is the double cover of SO13. Now also, and that is probably what mainly sparked this whole thing in physics, is that in Young-Mills theory and its generalizations, I mean, not, okay, anyway. So this is non-abelian gauge theories. This is where the vector potential, the covector potential of your, in quotation mark, electrodynamics, all of a sudden is Lie algebra valued. Okay, that's non-abelian gauge theories. So I should probably write non-abelian gauge theories. But in the standard model of particle physics, that would be, for instance, SU2, or it could also be SU3. So this would be, say, roughly speaking, the electroweak theory, and this is the strong interaction. These guys, these theories can actually only be properly understood, and the subtleties in there by considering principal fiber bundles. That's in Young-Mills theory. And but then, not least, well, that's not exactly physics. So let's say in mathematics. Well, studying these principal fiber bundles is, if you study the twists in that bundle, how the how the fibers twist. You know, it doesn't need to be a trivial bundle. Studying that, you learn a lot about the manifold, and in particular, there is a field called K-theory in mathematics, one hears a lot about. And in K-theory, roughly speaking, the cohomology groups of some manifold, and you heard, I told you about the cohomology groups, right? The cohomology groups of some M, some manifold M, are there essentially defined as the various bundles one can construct over M. And principal bundle techniques and bundle techniques in general are of course important there. So this is really something that permeates a lot of mathematics, differential geometry anyway, and also if you take differential geometry, so let's, in differential geometry, I told you that defining what a tensor density is may be a bit tricky without the bundles, and indeed what you look at a bundle a principal bundle whose fibers are the general linear group of the appropriate dimension. That's the so-called, you make this into the so-called frame bundle, and then you can define very easily the corresponding associated bundle on which this GLDR, where it acts on the fibers, which are in principle tensor fibers, but the GLDR acts with an additional determinant factor, and that's then the densities. So also kind of this heavily used instrument of tensor densities in differential geometry, especially also in general relativity, you also understand it properly by understanding principal fiber bundles and the corresponding associated bundle. So this is really lots of motivation, which at the moment you don't understand, but what you do understand, there's a Lie group, 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 a Lie group. Okay, and that's the principal fiber bundle, and that we want to develop. Okay, so this is the motivation. Please mention it in the evaluation. And then we come to 5.1. We need to prepare this whole business, and that's Lie group actions on a manifold. Lie group actions on a manifold. So this is a topic we could have discussed under the chapter 4 heading of Lie groups, but in fact it really fits here so well. We have it as a preparation 5.1. So what's a Lie group action? Definition. So let G with its blob be a Lie group, and let M be a smooth manifold. Then a smooth map with the interesting name arrow to the right that takes an element of the Lie group and takes an element of M, of the manifold, and maps it to an element of the manifold. How can this be smooth? This is smooth, that is smooth, so you can make the Cartesian product into a smooth manifold. Then you have a map from a smooth manifold to a smooth manifold. You know under what circumstances this map is smooth. Then a smooth map, Gm to M, satisfying two conditions, satisfying first of all that if I take the identity in the Lie group and I let it act on a point P in M, like so often if a map depends on two, it goes from a Cartesian product to somewhere, we put this in between there. Okay, it's like the addition, you know this from elementary school. So that actually, if the identity act, that yields P again for all P in the manifold, so the identity does nothing. And the second property is that if you act with some group element G1 on P, then you get back an element of the manifold, and then you can act again with an element G2 on the result. You may feel more comfortable having the brackets, but you don't need them if you read this. Only one way to read this expression. Anyway, and you require this be G2, G1, so you keep the order G2, G1, and that, of course, goes with the blob, and that acts on P. So you can act one after the other, or you can act at once with the product. Okay? Any such smooth map is called a left G action. So a left action of the Lie algebra, of the Lie group G, a left G action on the manifold M. And that's a central notion we're going to use. Okay, example. Questions so far? Okay. So let's have an example. So let G be some Lie group, okay? And I can choose as the manifold, I can choose a vector space, and not any, I choose this representation space of G that comes with a linear representation, capital R, that takes the Lie group into the endomorphisms over this vector space. Well, and we said we have such a representation. We studied such stuff before, right? We studied representations also of the Lie group into the endomorphisms. Well, actually, it was called the GL on V, because we need this to be invertible. And we can, of course, therefore define a left action of G on a representation space here by letting G act on a little vector, by definition, by using the representation of this element and let it act as a linear map on the vector. So that is representations of G on some vector space, like you usually find it in physics, in the introductory lectures, is a very special case, or are a very special case, of left actions, left G actions. Okay? So one is almost tempted to say what we get here are nonlinear representations, but nonlinear would somehow suggest it could be linear, it just is not. But in fact, if you take a general manifold, you don't have a vector space structure in the first place, so you wouldn't even know what linear means. So calling it nonlinear is somehow misleading. But it's something like this. You loosen this restriction that you act there. Okay, so that's this. Now we have immediately another definition, and that's the definition of a right action. And very often, if you can let it act from the left or from the right, it's a matter of convention. Of course it is, but if we talk about principal bundles, we'll always take right actions. And if we will then talk about fiber bundles on which the same group acts, we'll actually talk about left actions of this group. And this plays nicely together, the right action and the left action. That works fine. Okay, so really in principal bundle theory, we use right actions. And if we then go to the associated bundles, we use left actions. So we should write this down once. Similarly, a right action, now you can guess what the symbol is. It's the arrow like this. A right action takes M cross G, opposite order of course, into M, such that, well, the first one remains that you act on any point with the identity. And you see we now really write the group element on the right. So we take the word right action serious. That has an advantage you'll see in a second. This is again P for all P and M. And the second requirement is that if you act on a P with some G1, and then you act on it with some G2 from the right, again for your comfort only, I put these brackets, then this indeed is P, and now it's G1, G2. But like before, the order here remains here. And before it was G2, G1, but only because if you come from the left, you act first with the G1. G1 is the one that acts first, and then comes the G2, but that gives you the opposite order here as well. Okay? So, but this is important, and that is why it's so convenient to really write this from the right, because you can always keep the order. You don't need to think about it. Okay? But it's really something different. Okay? Such that you have this, and everything else stays the same as it was before. This is called a right action. Okay, I don't need to spell this out in every detail. Now, we can make an immediate observation, and that is let this guy be a left action. Then we can actually define a right action from it, then define, so you've got to be careful which direction this guy points, then a right action which goes from M cross G to M can be defined this way. I act on a point from the right, and this I define by taking the inverse of the group element, which always exists, and I let it act from the left on P. So from the left, so first, until you adjust your glasses, this is the new guy, and the white one is the old guy. Right? So you define the new guy in terms of the old one, you define the right action in terms of the left action, then this is a left action. It is a right action. And it's crucial that you take the inverse here. So let's show this. So what do we need to show? Well, quite obviously, so I need to act. Where's the new guy? Okay. So for any P, I act from the right with the identity. I know by definition this is the identity inverse, but that's the identity acting from the left on P, but that's P. Okay, so the first property here of the right action is satisfied. We should also check that it's a smooth map, because this is supposed to be a smooth map. Why, if the left action is a smooth map, which it is by definition, why is the such defined right action also a smooth map? Please argue why. Well, because taking this inverse is a smooth operation, because we're on a Lie group. So this is one of the points where this property that taking the inverse is also smooth. Well, of course, it was implicitly important before, but this is one important point. So this needs to be checked as the 0th point. Okay, so but then we have this, and now we check, we act on P from the right with a G1, and then we act again from the right with a G2. And well, we now use the definition, first use the definition in brackets, that's G1 inverse acting from the left on P, and then on this from the right we still have the G2 acting, and that's of course the G2 inverse acting from the left on the G1 inverse acting on the left from the left on P. We have this guy. But of this guy here, we know that G2 inverse blob G1 inverse acting from the left, that this is true because it's a left action. And then we know that the inverse of a product is the the product of inverses is the inverse of the product, but with the order exchanged. It's also clear in any possible context, also here for the Lie groups. And that acts from the left on P. But this, again, by definition of the right translation, is the P on which we have acting from the right G1 blob G2. And this is precisely what we required. And you see that the inverse is important to flip here the order. If we didn't have the inverse, the order wouldn't be flipped. It wouldn't be a right action. And there you see really right action something different than the left action. If right and left actions were the same, then I could have defined that it would be just a different notation. You can say, well, but I can write it on the other side, right? It's just flipping the symbol. But a right action, because of this property, of these properties and keeping the order and is a different thing. Okay? Good. That's the right actions. Once expressed in terms of principal bundles, principal fiber bundles, and associated bundles, we will see that the recipe of labeling a basis of a tangent space, a basis E1 to E dim M of the tangent spaces of some manifold by lower indices. Well, I told you this is just a convention, and the components of a vector x in TPM by upper indices and the corresponding transformation behavior and having the corresponding transformation behavior that if you define a new basis by some matrix A, M, A, E, M for all the basis vectors, and you correspondingly have that the new components of a vector are given by precisely the inverse of such a transformation, right? Why is this? Well, because then still the product, the linear combination of these E twiddles with the X twiddles is then still the same as the original components with the original basis, because the vector is the vector. It's just expressed differently. That's how we understood this A and A inverse before, right? Will be understood as a right action, of the general linear group in d dimensions on the basis, and a left action of the same GLD group on the components. We say, yeah, sure, that one must be the inverse then of the other. That's the relation. These guys, this will be understood as the frame bundle, okay? This is the bundle of frames, the bundle of bases that transforms in a certain way, right? That's then the principal bundle we're going to define. It's this frame bundle, and then we'll have just a a bundle of R4 fibers, say, that's just the components on which this group also acts. Okay, so this whole business in physics about thinking of components and how components transform. You see, this is how this is very often defined in physics. A tensor is what transforms as a tensor does. Okay, but in order to really say this precisely, what it means, a tensor is something that transforms as a tensor, or tensor components are things that transform as tensor components, would be the more precise formulation. In order to really say this precisely, you need principal fiber bundles. Okay, so this is this view. Good. So this is just a remark to make to show you where we are going. Now there's one more definition I would like to provide. Now assume we have two Lie groups. G with a blob and H with a little square. Okay. And let's assume we also have a Lie group homomorph. No, let's make it a bit more tricky. Let's have two Lie groups and a Lie group homomorphism. A Lie group homomorphism. Let's call that guy rho. It's not a representation like before, but it's now a rho that takes you from one Lie group into the other Lie group. It's so Lie group homomorphism means it's a smooth map because we always took smooth Lie groups, and it's of course still a group homomorphism. You know, meanwhile, how that works, that the blob product can be taken and then you apply the rho. You can first apply the rho to two elements and then take the square product. It's a Lie group homomorphism. Is this what I want? Yes. And let M and N be two smooth manifolds and further let's have two left actions, namely one that we denote like this, a left action, so it's G cross M into M, and the other left action, let's take a filled triangle, is from H cross N into N. So two Lie groups, two manifolds. Between the Lie groups you have a Lie group homomorphism and you have these two manifolds, and let F from M to N be a smooth map. If you have all of that, then F, the map F, that takes you from one manifold to the other, is called rho equivariant. Rho equivariant if let me try to squeeze the diagram here. Yeah, if so we take G cross M and we take M. How do I come from G cross M to M? Well, by virtue of my empty left action. I take H cross N to N by my solid left action. I have this map F that goes from here to here. How can I construct a map from G cross M to H cross N? Well, I can construct it by taking rho cross F, where this cross means the rho eats the first factor and the f eats the second factor, and the rho eating the first factor produces the first factor, f eating the second factor produces the second factor. Okay? Very simple. I think we did this in statistical mechanics. We use this a lot. Then f is called rho equivariant if this diagram commutes. Again, what does that actually mean? It means you can go this way or you can go that way. So let me first write down this way. That means you let G act, some G in the group, you let it act from the left by this empty left action. You let it act on some M, so some little m is a point in M. I rather write little m here. You let it act, and then you take the function f to map it, and this is supposed to be the same as you first map the G by rho, and you map the m by f, and then you take the result and you use the solid action. Okay. So it's a new word, rho equivariant, and what does it talk about? Well, it talks about if you have two manifolds that are equipped each with a left action. You have the manifold n equipped with this action, the manifold m equipped with this action, not of the same group, but by groups that are connected by a group homomorphism. So what we're talking about here, rho equivariant maps between manifolds are maps between manifolds that preserve a left action that's given on the respective manifolds. So it's again the same principle. We're talking about the structure preserving maps between manifolds, only that the structure given now is a particular action of a Lie group on one manifold, a particular action of a homomorphic Lie group on the other manifold. Okay? Right. So this is rho equivariance, and this plays a role in physics. So you can do this without this rho. You can say that this H is the same as this G. But in physics, for instance, you have here the Lorentz group, SO13, but you do not. But now you want to compare this. What happens if you replace it, or if you map it? Not replace it. If you map it by a homomorphism into SL2C, which is the spin group, right? And you need to know if you rotate your measurement apparatus, which you do by Lorentz transformation, right? I mean, I rotate it, or I move it put it into a moving system. It's a Lorentz transformation. But now this apparatus is, for instance, constructed to measure the spin of some object. Okay? But then you need to know what this rotation in physical space, or this Lorentz transformation in physical space, what it does to a spin particle. So you need to have an embedding of SO13 into SL2C. That's a 2-to-1 embedding, right? And this is where something like this comes up. Okay, so it looks excessively mathematical, but it's real. It's the real life, at least in theoretical physics. Okay, good. So that's the equivariance there. Now, this just for completeness at this point. Now we have further important notions which we're going to use heavily. So definition. Let this guy G cross M to M be a left action, okay, on some manifold M, obviously. Then we define A, the orbit of a point. So for any point P in the manifold, we define its orbit under the action as the set. So the orbit, well, let's choose a curly O. It's not a topology, it's an orbit. It's the orbit of the point P. What kind of guy is that? That's all the points Q in the manifold which you can reach by starting from P and acting on it from the left with some G. So for all for which there exists a G in G, such that G acting from the left on P produces the Q. That's an orbit. Well, let's make an example right away, although we're in the middle of the definition. Example, let's say the manifold is R2, and let's say that the group is SO2, and let's say that the left action of G on a point in R2 be defined as the vector representation of this guy acting on the point P. Well, P is just a pair of numbers, P. Well, I write in quotation marks because I need to choose coordinates to do that. That is, if you have something like cos phi, sin phi, minus sin phi, cos phi of P1, P2, something like this, right? We know how that works. And that's, of course, simply the rotations of the plane as they act in the vector representation. So that's what you usually call the rotations, right? And now take this point here. What's the orbit of this point? This point be called P. In the orbit is any point you can reach from there by action of the group. So it's all the points on this circle. But this point you cannot reach from there by action of SO2 of this particular action here that I wrote down. So this guy here, this whole set, is the orbit P. So the orbits are subsets of the manifold. Okay? Right. All the orbits are all the circles, but there's also one point here, which is the orbit of itself, right? It's also the orbit of that point. That's not a circle. That's just a point. Okay? So we have this. Well, once we have that, we can take B, but it actually belongs to A. We can define an equivalence relation. Let P equivalent Q, so these are points in M, by definition, if there exists a G in G such that P equals, or Q equals, doesn't matter because we can take the inverse, G from the left on P. So in other words, they are called equivalent if they lie on the same orbit. So this point and this point are equivalent, but that point and that point are not. Okay? So one can quickly check this is an equivalence relation. Equivalence relation. So it's reflexive. Why is it reflexive? Well, because the identity is always in the group. It's symmetric. Why is it symmetric? Well, because there's always the inverse in the group. And you have that if you act again with the inverse, well, let me write it down, it's because G inverse Q, if this is true, then G inverse acting on Q is G inverse acting on G acting on P. But this is G inverse blob G acting on P. That's the identity acting on P. That's P. So you can write this the other way around, and the inverse always exists. So there is such a group element, in that case the inverse, and you can also check that it's transitive. Let's not do that. So this is an equivalence relation, and if you have an equivalence relation, you can consider the equivalence classes. So you can take the manifold and identify all the points that are equivalent under the equivalence relation. So that's the quotient space. And because this quotient space has been defined using only this group and this action, we very often write instead it's M mod G, right? It's just another notation that because you do not always have to carry through this construction, because once you know it, you say, well, the group identifies certain points by being in the same orbit, and this is then called the orbit space. And indeed, the equivalence classes are all these circles and this one point. So one element of the orbit space is, well, exactly the set of points that makes an orbit. Okay, so you have a foliation of this space into lots of orbits. It's like always. This is a very particular example, and this orbit space will play a very important role in the principal fiber bundle theory. Okay, so we have this. Right. Okay, so then let's have C. We define for any point P, any P in M, we define the stabilizer. That's now again a set, let's call it S sub P, because it depends on the point where you are. But while the orbits were a subspace of the manifold, the stabilizer is a subset of the group. Okay? And the stabilizer are exactly those elements of the group that keep the point that you fixed invariant. So the question, the stabilizer are all those elements in the group that do not move the point you chose. Okay, that depends on the point, and that's obviously a subset of the group. So always keep that in mind. Orbit subset of the space, stabilizer subset of a group. Okay, so again, example. Well, let's take exactly the same example. So we have here the rotation, so as before. What's the stabilizer of this point under the action we wrote down before? Which transformations in SO2 leave this point where it is under the given action, which rotates every point around the origin? Only the identity, that's right. So if this is the point P, then SP is simply just the identity. And this is true for any other point. Any other point, namely? The origin. Only this point, Q, the origin, what's the stabilizer there? Everything. It's the entire group. That's right. Okay, so that gives rise to a definition. An action, let's say this left action, but obviously you can do this for the right actions too. An action is called free. It's a free action if separately for every point the stabilizer at that point just consists of the identity. So obviously this SO2 action here is not a free action. A free action is such that every point is stabilized only by the identity.
Stabilization with the identity, I can also choose phi out of, say, is phi restricted to 1 to pi? Because otherwise...
No. But look, the stabilizer is the set of all group elements that keep it the same.
But I want to say that I can choose another element of the group in the respective representation that gives me the same point. In the representation, I choose the identity and I choose...
Yeah, very good. But what did we do here? We, you're now talking about, okay, look, so you see, this is why I didn't want to write this down. But it's a good question, because what we have here, the phi, it's a very good example with what we said before, because this is, of course, exp of phi times the endomorphism given by this generator acting on P1, P2, right? Now, this guy here, so the group is compact, right? SO2 is a compact group because the group manifold is S1, is a compact space. Because it's compact and we use the exponential map, it cannot be injective. That means we hit the same point several times. And that's what you're saying. You can plug in phi equals 0, and then for phi equals 2 pi, you hit the same transformation again. And for 4 pi and for 6 pi and so on, you hit it again and again and again. Now, this, however, doesn't speak about, it really speaks about the group. So once you come back to the same element, it's the same element again. So every time you choose phi equals 0, 2 pi, 4 pi, 6 pi, and so on, you hit always the identity element. So there are no others than the identity that do that, right? And the misunderstanding there comes, or the feeling there must be more elements, is because of this non-injective generation of the group elements this way, which is here in matrices expressed that way, right? I mean, of course, you can also explain, yeah, you can say, well, it's the same transformation that acts, but okay, so this has exactly to do with what we said before. Okay, so an action is free. Question: can ever be an action that we defined in terms of a linear representation, can that ever be free? Well, this one is not. Now, the answer is can never be free because a linear transformation, a linear action, endomorphism space here on them, will always map the 0 vector to the 0 vector. That's a linear map, always does that. So hence, whenever I generate a Lie group action on a vector space in terms of a linear representation, it cannot be free. Okay? What about the translations of the plane? I can translate in this direction, that direction, or any linear combination of that. Is that free? Should be, no? Because you always find a transformation, I mean, any transformation moves a point away from where it is, apart from the one that doesn't do anything. So translations would be free. Okay, that's the free translations. So now free action. So there are other notions like transitive actions and effective actions and so on. They're all useful to define, but we're not going to need them immediately, so I rather not confuse them with them. But if you stumble across them, effective actions, transitive actions, they're all defined along similar lines. So it's nothing to be afraid of. For principal fiber bundles, we really just need the free actions. So what's the crucial property of a free action that we're going to use? So this is observation, and I'll ask you to show that on a problem sheet. Observation, if this is a free G action on M, then each orbit OP, so can label them by different base points, each orbit is as a smooth manifold the same, so it's diffeomorphic to the group. Okay. So for example, if we had taken the manifold not to be all of R2, but we take out the origin, okay? And nevertheless, we define a left action that lets SO2 act on this guy by pretty much the same definition like we had before, by employing the vector representation we wrote down last time, I think, of this group element as it acts on this pair P1, P2 that lies in here. But you see, now I took out of this M, I took the origin out. So it's no longer a vector space. But of course, I can still act with this on everything, but I just removed the origin. But this is no longer a linear representation because it doesn't act on the full vector space anymore. Okay? So it's now really only a left action. I mean, it's a very trivial modification of a linear representation, but nevertheless, and you know, now I took out the origin, and everything else remains the same, but that means that the orbits are like this. And you know, so these are the various orbits, and you know, because I took, so I should indicate it's not a circle, this means this has been removed. Huh? And you know, the only point whose stabilizer was not the identity was this origin. So now this action is free because for any point that is in there, the stabilizer is the identity. And now you see the orbits are the circles. And each of these circles is, of course, isomorphic to SO2, because SO2 is the Lie group that's built on the circle as the underlying smooth manifold, but with an additional group law, how you, but as the underlying, this is a nice, so and hence, so every orbit is isomorphic to an S1, well, that you can see, but S1 is the group manifold that underlies SO2, so in a sense it is SO2 seen purely as a smooth manifold, right? It's child's play. Very simple, okay? And that's the purpose of considering, or one of the purposes of considering free actions, that you know immediately, a free action, the orbits are the group, isomorphic to the group. Okay. So then, after these preparations, we can come to the central definition. So principal fiber bundles. It's also the chapter heading, but well. Definition. A bundle. Well, a smooth bundle. Whenever we're talking about bundles now, we assume everything is smooth. The spaces are smooth, projection maps are smooth, all the maps are smooth. So should I forget to mention smooth at some point, you may insert it. So a bundle, what was that? A bundle consisted of a total space, a projection map, and a base space, if you remember. Such a bundle is called, a bundle is called a principal G bundle. Principal G bundle. If, well, what do you need? You need that E, well, E is, okay, so there's this terminology that one says E is a right G space. But what is a right G space? That means you have E equipped with a right action of G on it. Okay, so let's introduce the terminology. So if E is a right G space, right? But this is just terminology which in principle one doesn't need, it's just very convenient. That means E is equipped with a right G action. Oop. So we have such a thing. B, this right G action is free. So this we certainly want to have. That makes the principal G bundle rather than just having a right G bundle. This is free. And now I need to say, okay, I have a bundle E pi m. There is no site of any G anywhere. Okay, so when do I call such a bundle a principal G bundle? I call it principal G bundle if E pi m is again another symbol for the bundle. If this bundle is as a bundle isomorphic, but as a bundle. You remember when a bundle was isomorphic? Maybe I remind you in a second. But first the definition. This is called a principal G bundle if as a bundle it's isomorphic to E. So I take again the same total space, but I compare with the bundle that's built from the same total space going down into the orbit space of this total space under action of the Lie group. Okay, so I have a manifold E, the total space is a manifold, and I have a right G action on it. The G action is free. That means every orbit of this G action is the group itself, is isomorphic to the group. Okay, and I choose this E modulo G is the orbit space, is the space of all orbits, and because the fibers are always the same, this is a fiber bundle. The fiber of this bundle, and there is a projection map rho, and that's the normal projection map that you take from a set into the quotient set. You remember where you send a member of the set to its equivalence class. That's this map rho. Okay? So you take that guy, you go down here, and because the action is free, the fibers, so the row inverse of a point down here, is always the entire group. Okay? But we'll write this down in a second. But this is the definition of a principal fiber bundle. So let me write down the observations, but they're not part of the definition. Observation. So I should say, so this row is just if you have a map from E to the quotient set, it takes a point, yeah, little e is bad here, it takes a point, I don't know, epsilon in E, it takes it to the corresponding equivalence class. That's this map rho. Okay? So an observation is since the right action is free, it follows that the fibers of this bundle here, so the row inverse of some, well, equivalence class of epsilon, I don't want to invent yet another symbol, is diffeomorphic to the group, to the Lie group. Okay. Okay, but this is just an observation. So again, a bundle E pi m is a principal G bundle if I know of an action on this E, I go down to the orbit space, to the space of orbits, okay, by this canonical projection map, and if as bundles they're isomorphic. So maybe I should recall, what was the definition of a bundle M pi, or E pi m, and the bundle E prime pi prime m prime, so another bundle. When were they isomorphic? What was the definition? Well, you needed a map U up here, and you needed a map F down here, both of them smooth. So this, so I should write E pi m isomorphic as bundles to E prime down with pi prime to M prime. By definition, if and only if, here there exist smooth maps U and F such that, well, actually diffeos, there exist diffeos, smooth and invertible, well, you can go in both directions, such that pi prime after U is the same as F after pi. So I could also say there exists diffeos UF such that this diagram commutes. Okay? So, as always, you have an object that consists of three elements, this, this, and this. And if you want to show, going to define an isomorphism to an object of the same type, you better map every of the objects by the isomorphisms of what they are. But if there's additional structure here, this pi, you better also preserve the structure. And that's then, this is always the same. So in a sense, one doesn't need to remember this. One can always reconstruct it by thinking about what is structure preserving. Okay. And now you see in which sense, I said in the beginning that a principal fiber bundle is a bundle which, very roughly speaking, whose fiber is the Lie group. Well, a principal fiber bundle is isomorphic as a bundle, which is a G fiber bundle, right? It's just isomorphic to it, but you know that in this isomorphism, here the G is not immediately visible. Only that I know that the G can act on the E, but this is the definition of a principal fiber bundle. And this is the simplest definition you can give that does what you want. So I encourage you to revise until Thursday, until next lecture, to revise the definitions of pullbacks of bundles we had, and sub-bundles, restrictions of bundles, and so on, to revise all of this because we're going to need it in our further discussion of the principal bundles. So we'll now consider a particular example for a principal G bundle. And this example is of the utmost importance in differential geometry, and that's the so-called frame bundle, which goes by the name LM. And this is defined as follows. So if first at a particular point x in M, we consider the following set. We look at the L sub x's of M, which are a ordered dim M tuple of E1 to E dim M, with the property that the E1 to E dim M constitute a basis for the tangent space. So E1 to E dim M are a basis for the tangent space Txm at precisely this point. And that's not the frame bundle yet. That's the space of frames at a point x. So a frame is a basis. We could call this the basis bundle, but it's just tradition to call it the frame bundle. Okay? And so we have this kind of guy, and this is obviously this is obviously isomorphic to GL dim M over R, because you certainly remember from your linear algebra classes that if you take the vectors of a basis and you express them in some, say, over R dim M in terms of the canonical basis, you get column vectors, and if you put these columns next to each other, you get an invertible matrix, right? So that's definitely the case, and we'll invoke that isomorphism in a second. But then we define the frame bundle as Lm is the disjoint union over all the x's in M, LPM. Now let me make a comment on this, because there were some questions, I was told, about this kind of disjoint union. This is really the precise definition, and the idea is the following. Go back to the tangent bundle. An aside is the following. So we defined the tangent bundle in similar fashion. We had the disjoint union over all the x's in M, Txm. And so that means you think for instance about part of the sphere. So you have the point x here, and you have the point x prime here, and there's the tangent space Txm, and here is the tangent space Tx prime m. Now, you can think, I mean, these are entirely different spaces, right? And so you can think of the guys in here being apples, and the guys being in here being pears. So now I put all the apples and pears into one bag. That is what the union is. And now I close my eyes and pull out an element of the union, and in my hand I have an apple. Is there any doubt where the apple comes from? Well, I mean, I have nice apples, there's a nice apple, there's a not so nice apple, and I have big pears and small pears and everything, okay? But if I have an apple, I have an apple. So if I reach into this bag of this that is represented by this union, I pull something out, it's an apple, so I always know it comes from this space. So that means if I take an element x from the tangent bundle, it is a vector. The x is a vector, but nevertheless, I always know, if it's from here, then I know there exists a unique x such that x comes from T sub xm, and hence I can define a map, a projection map, that takes an x and assigns to it the small x, which is the base point where it comes from. Okay? Hence, a construction of the type union over all x Cartesian product Txm may look good because you say you make this explicit, you make this point explicit, and you then have in here pairs, well, not these pairs, the other pairs with AI. You have in here pairs of points and tangent vectors. That's okay. The point is, it doesn't solve your problem that you know kind of what dimension this space is and so on, because this, first of all, is just a set. And as a set, it doesn't have dimension. You need to make it into a topological space and then into a topological manifold in order to start talking about the dimension of this guy, because dimension is only defined from that structural level onwards, right? So we do this, and then, so this was the aside, hopefully not more confusing than enlightening. But this is the definition we want to make in complete analogy to the tangent bundle, and then we equip this guy. We want that this guy inherits an atlas, say a smooth atlas, because we just work in the smooth category here. So we equip this with an atlas, equip Lm with a smooth atlas inherited from the smooth atlas on M, which must carry a smooth atlas because we assumed M to be a smooth manifold. And this works in complete analogy to how it worked for the tangent bundle. You take elements from here, you express them in a basis-induced chart, in a chart-induced, sorry, the other way around, in a chart-induced basis, and then you decompose every single one of them, and you get numbers E, A, B, no? Like a square array of numbers that coordinatize every single one element in this LXM, and those you use as coordinates of this frame bundle. So you do this precisely the same way. I don't think it's worth spelling this out again because it's a complete analogy. And then you find, of course, that the dimension of the thus produced smooth manifold Lm must be the dimension of M, that's the base manifold, plus the dimension of M squared because of this. So it's dim M times 1 plus dim M. Okay, so that's the frame bundle, and this is the frame bundle as a smooth bundle. No, there's something missing. What we still need is the projection map. So we define the projection map pi from Lm down to M, and this is now the apples and pears thing. So if I take an element from here, it's necessarily of this form. So let me write D for the dimension of M. It's necessarily of this form, but you kind of take this guy and then you look at it and you say, oh, it's an apple, so you know at what point it is defined, and this unique point you assign to it, right? So the logic is this is from Lm, and then you assign to it the x, right? And the point is there exists a unique x in M for which E1 to ED, the one you picked from the union, is an element of the LXM. So although this was from Lm, it's in particular an element of LXM because this is a disjoint union. And that unique x you take. And that's then the bundle projection. And so in total, we got that Lm with this projection map down to M is a smooth bundle. So obviously, in order to really show this in detail, you have to check a lot of things, but this is the sketch of what you got to do. Now we want to see whether we can make this frame bundle into a principal G bundle where the group G is exactly this guy GL. Okay. So, so second, maybe we start out here making this a bundle A. So then B, we establish a right GLDR action with this name on the total space Lm. Remember, this is the total space of the bundle, this is the base space, this is the projection map. So we establish this action by virtue of, so we define, so we take an element E1 to ED, and we wish to act on it with a GL transformation. Let's call it small g, but small g is an element of GLD. Okay? And we define this action as follows. G up M down 1, EM, comma, GM down 2, EM, dot, 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 up to GM down D. D is the dimension, EM. Okay, what are these GM1s, GM2s, and so on? GLD is all the endomorphisms which are on from RD to RD, which in this case, for simplicity, but this is perfectly fine, already represent by their matrices. So GMN, these are all the GMNs where these guys are in R, and MN run from 1 to D, and the determinant of this G, index up, index down, is non-zero. Well, that's our definition of GLDR, and we let it act on this frame in this fashion. Now what this of course is you have a basis, and now you do a general linear transformation, invertible transformation of the basis. So that means the new first basis vector, that's the new first frame vector after the action, is a linear combination of all the frame vectors EM you have, right? And it produces one new one. So it's the first one, it's the coefficients, the first collection of coefficients for this linear combination. This is the second collection of coefficients for this linear combination that makes up the second one, and so on. This is, of course, precisely how you transform from one basis to another basis. Okay? So this is the action of the GL group is doing this. Aha, good. So the question is this a free action? It's a right action, right? But the question is this a free action? What was a free action? A free action is one which at any point is such that only the identity, that would be the delta here, delta Mn, only the identity keeps this thing unchanged. And that's precisely what happens. If you just have one vector, and then I can find GL transformations that are not the identity, that keep the vector invariant. If I have two vectors, I still find GL transformations that keep them invariant. Well, in 3 dimensions it gets trickier. But now, okay. But if you have an entire frame, there is nothing you can do to keep every vector of the frame invariant. Hence, this is a free action. Well, that's now the intuitive argument, but obviously you can make this into a formal proof. So what we did, we could establish on this frame bundle a right GLD action. That's good. And so the question is this frame bundle, once the total space is equipped with such a free right G action, is this a principal G bundle? Is this a principal, so is LM pi down to M, and one should always say there is on here, there is also an action of some group. Is this a right action? Is a GLD principal bundle or principal GLD bundle, whatever. Okay. What do you have to check for that? Well, you've got to check whether, if you look at your bundle, whether you have a bundle map view that's an isomorphism, so there should be an inverse like this, to the same total space, but going down to the total space, and then you take the quotient with respect to the group you have here, okay? And if there is such an isomorphism UF between these two bundles, then you call this guy a principal G bundle. And of course, in order to check this, you need to have the action of this action must be defined on this LM. Now, what's the intuition of this? Well, this is the space of orbits. So you take an element in here, LM, and then you act with the entire group on a particular element. Okay? And that gives you the orbit of the group in here, and you mod these out. That means you look only at the set of all the orbits. Okay? But if that is then the same as the space M, well, at least if there's an isomorphism, then we call this a principal G bundle. Now let's see where this is the case here. So I take this guy, the LM, so that's a frame at every point in a manifold. And now I act with the entire group on a particular point. So I go to the manifold, I say this 3 space, go to this point here, and I put up a frame. Now, what's the orbit of that frame? Well, it's any GL transformation I can perform at this point. So I get any other frame. So if I ignore this orbit, right, all that remains is the point, right? And that's precisely this isomorphism we want to have, right? So indeed, I can go from any one frame to any other frame, and that's a free action. So this is definitely the case. Again, you can write this down in many ways, but it may be worthwhile in order to get the idea when something is a principal bundle, you have to check this first intuitively. Is this reasonable that it could be one? And then you write it down. Okay? So in this case, that is that. Okay. So another check here for the free action is you must be able within an orbit, so if you say you take the frame at a point, and that's supposed to be the fiber of this bundle, you must be able to reach any point in that fiber from any other point in that fiber, from another frame, by some action here, and in fact, because of free action, by some unique element G acting on it. Okay, so that's the intuition, and that's all the case here. So indeed, this is a principal GLD bundle, and that's very important. Okay, we'll so that, because this is how physicists say a basis is being transformed. Now, if a basis is transformed, then also the components of a vector are transformed, or the components of a tensor, or the components of a tensor density. Now, however, that we can't see here yet, because these vectors, tensors, or tensor densities will not be elements of this bundle. How would they be? They will be elements of a so-called associated bundle, a bundle that's associated with this principal bundle, and there will be a left GLD action on there. We'll do that later. So we can't take this example further at the moment, but later on it will nicely become the formal setting which intuitively you've been told probably from the first semester in physics of tensors in classical mechanics, the inertia tensor and so on. So at the beginning of this lecture course, I kept emphasizing that we always study the structure-preserving maps between objects, and of course that remains true. If we first recall that if you have two bundles, E down to M, with some projection map pi, and you've got another bundle E prime down to M prime with another pi prime, then we said a bundle map was a pair UF, where the U goes from the total space to the other total space, and the F goes from base space to base space, and we call this a bundle map if F after pi was pi prime after U, or in other words, if this diagram commutes. Now, we want to define the notion of a principal bundle map, and a principal bundle certainly is a bundle, but it has additional structure, and that we got to take into account. So I start a little lower here. So if we have a principal bundle P, so first here the left-hand side, P down to M, and another principal bundle P down to M prime here. So let's not do this at the moment. We have two principal bundles. Then we also have the action of a group, the right action of an entire group on this bundle here. And on this bundle, we have the right action of an entire group. Let's say there are two principal G bundles. So two principal G bundles, meaning principal bundles with respect to the same group, but otherwise they're different. For instance, this here is also the primed action, because the group may act on this total space entirely differently from how it acts on this total space. We, however, want to assume that it's the same group acting. But even that needs to be generalized, but let's do it this way. And of course, it then takes you from P to P and from P prime to P prime. So a principal bundle, if you want to be very strict, shouldn't only be denoted by this, because there's always this right G action on the total space. Let's not forget that. So sometimes this is suppressed in the notation, but it shouldn't be. So, but that means if you now consider a map between these principal bundles, it first and foremost must be a bundle map, certainly, because it's a bundle, but there is some more stuff to be preserved, and you still want the same U. Well, between P and P prime there's a U. Well, let's repeat this U, but there is now not only compatibility down here, but there's also compatibility up here, so we want this entire diagram to commute. It's the only natural thing to do, right? Okay, so we say this is so UF is not only a bundle map, but it's a principal bundle map. That's different from a bundle map. It seems like a subtlety, but it isn't. It's different from a bundle map, a principal bundle map. So the requirement is that this guy commute. Okay, we require it commute. And then we have, that is, well, the thing from down here, always almost not worth mentioning, f after pi is pi prime after u. That's just the bundle map aspect of it. But we also have an equivariance aspect of it, okay, how it behaves under the action of this group. But this terminology is not necessary if you just remember this needs to commute. So we can read this off here. So we have that u after the action. Now, in order to write this properly, we say u of a point P on which a group element G acts. So I pick a point P, I act with a particular group element small g, and I get another point here, and then apply the u. This should be the same as applying the u to the same point P, and then after that acting, of course, with this primed action, because we're here acting, but with the same group element. So obviously this is supposed to be for all P in P and for all G in G. That's it. That's a principal bundle map. Now, any questions here? No, that's straightforward enough, right? So we have an important generalization of a principal bundle map. It's in a sense the maximal generalization. So I take a principal bundle, P pi down to M, and I equip it with a bundle action with respect to a group G. This is quick notation, but you know what I mean. I go back to P, and now I take another principal bundle, P prime, down with pi prime to M prime, and I go up here to P prime, all right, and I have an action pi prime, but it's a different group G prime. So really two entirely different principal bundles, even a different group G. Can't be more general, right? Now, in order to talk about a principal bundle map now, you need an extra ingredient, and the extra ingredient that you have to provide alongside, so it's nothing to do with this diagram, it's a new diagram, you have to have a way to relate elements in G to elements in lambda, and that we could call rho. Okay, so it's a map rho. Now, because this is a Lie group and that's a Lie group, what would we very likely require of rho? Well, that it's smooth and a Lie group homomorphism. Okay, so we would require that this be a Lie group homo. Okay, and so Lie group homo, we recall, is that you can apply rho to a product of a little g1 and a little g2 with a blob, and the blob is the blob in G, and that this be the same as the rho of the g1 with a blob that's now in G prime and the rho of g2. So this is an additional piece of data we got to give, an additional datum we got to give, and then you have a U and the F, and you can ask the same question again. When is this, or how would we define this to be a principal bundle map? And now the requirement is that all of this commute. So again, F after pi is pi prime after U, bundle map aspect. And now here we can employ this. We can say, aha, U after this action, so U after this guy here acting on a point P that we take from here. This now, well, it's a requirement. This now be first U of P, you first go here, and then you act with this guy, but now there is another group with respect to which this is an action, but you have an element from the group over here, so obviously you now invoke the row first, and to make an element from the G group into an element of the G prime group so that it can act from the right. It's totally obvious. Once you draw the diagrams, everything becomes child's play. Okay, so and this is the important generalization. So this is then called a principal bundle map. Like before, but now you take it very seriously that you can have two entirely different principal bundles.
Question to the notation. Is a bundle morphism the same as a map in your talk?
That's right, that's right. So a bundle morphism is a bundle map. That's right, yeah. So, well, morph is form, and so a morphism is a form or a structure preserving map, and that's the game we're playing all along. That's right. I think we called it bundle morphism before. Yeah, that's it. Okay. Good. So we have this guy. Now the question is this generalization for generalization's sake, or is there an application? And there's a very important application of this generalized notion in general relativity. And that is, in general relativity, we would often look at the frame bundle over the space-time manifold M, okay? And this is this guy, and the group that acts on there, so that would be the P, the group that, the M is the M, right? And the G is GLDR. Aha, but then if you have a metric, you can actually look at SOD. And very often we'd look at SO1, 3. So this is the Lorentz group, okay? So we would restrict our group to the Lorentz group, and that actually is equivalent to the introduction of a metric down there. Because now you can say this frame and that frame, only the ones that are related to each other by a Lorentz transformation make the orbits. Okay, but then you have to restrict this to only such frames and so on, so that you can do. And then you can define and the action of the Lorentz transformation on this guy, well, that's like formally like the one we had before. Then you can do the P prime, and this is now not the frame bundle like we had it, but it's the spin frame bundle. So it's the spin frame bundle. Right? And there you let the group G prime act, which is SL2C. And indeed, there is a row map that takes you from SL2C over to SO13, right? And it's a 2-to-1 map. Right. Okay. And we'll come back to this. I just mentioned it at this point, and then you have a principal bundle map between them, and then you know, well, if I rotate my measurement apparatus, which I think of classically, if I perform a Lorentz transformation on it, what's the corresponding spin transformation on the spinners, right? And that is well, we'll only be able to show how that works in detail once we have associated bundles, but that's the idea. So it's of the utmost importance in general relativity in order to understand how you put spinors on a curved manifold. Because you cannot, there is no spin representation, at least there's no finite dimensional, unitary, and so on, irreducible spin representation of GL4. You got to restrict to SO13, so you first need the metric in order to then talk about spinors. Whereas in order to write down tensor fields, you don't need a metric. Tensor fields are there because the manifold is smooth. But finite dimensional spinor representations first require a geometry before you can even say what a spinor is. And this is encoded here. And then once you transform according to this transformation, your local frame in the frame bundle, in the spinor frame bundle, you got to use this transformation. And this principal bundle map physically tells you once you do this here, then you got to do the other thing over there. And what the other thing is determined by this structure. But again, the action on spinors and tensors we can only discuss once we have the associated bundles. Okay, so should the remarks remain mysterious, have patience. Okay, good. So now we come to a little lemma. Sure, please.
If you have this given map U, can you come to the map of the groups to the row?
Can you come to?
If you have a given U and you want to know what the row you need to transform into unit groups.
No, the row is an extra piece of data you need.
Okay, but there must be a connection between them, so.
Yeah, but the connection is only established by the requirement that you must have chosen your U and your row such that they satisfy this requirement. Okay, but there is no way to say, well, once you have the U and you know all the other stuff, what is the row that does this? Because there might be several different rows that make the whole thing into a principal bundle map of this type. So because there may be several different ones, that immediately says that you cannot determine the row from up there. Certainly it restricts the choices of row. No, it doesn't even restrict the choice of row, because for any Lie group homomorphism, you can impose this condition. But you say you have already chosen the U specifically. Well, yeah, it may restrict the rows, but there will be certainly different rows that do the same trick, I guess. Okay. So it's here the idea is really you prescribe all these data and then you impose the condition. And that's also the case in practice, like in our example here, that you already know how SL2C can be mapped into SO13 and so on. Okay, good. But again, I mean, in particular circumstances, it may be possible to restrict this totally, but in general, I don't think it is, in full generality. Okay. So I have a little lemma. So principal bundle maps are a stronger notion than a bundle map, and this is a consequence of this stronger notion is expressed in the following diagram. P to P prime. So we consider again two principal bundles, and we have them over the same base manifold, M. Okay? So in the sense that this guy here is supposed to commute, then we have a map U between these two. And we have a pi that goes here, and we got a pi twiddle that goes there. And the claim is that any such principal bundle map is an isomorphism U. Okay, so this for any such principal bundle map, U is an isomorphism, but when isomorphism is depends on what kind of structure this is. So if they're smooth manifolds, it's a diffeomorphism. The important thing is it's invertible, right? It's one-to-one and surjective. U is, let me write, a diffeomorphism. Stop. And I hope you note that the color coding serves no mathematical purpose, but it's a Christmas tree. So now let's try to prove this. So what do we need to show? We need to show that U, first we need to show that U is injective. And then we show that U is surjective, and then one can also investigate whether all the constructions preserve the smoothness, and that will also be the case. But if it's injective and surjective, it's invertible, and then the rest follows. Okay. So the interesting part is U is injective. Aha. So now how do we do this? Well, we need to start out with assuming that we have a U of a point P1 in here, and that be the same as the U of another point P2 in here. And of course, in order to show that the map is injective, we've got to show that from here it follows that P1 equals already P2. So how do we do this? Well, we have to take everything. Okay, yeah, my Christmas tree. Okay, so the Christmas tree is a bit too small. So we go from here to P again, and from here to P prime, and then there's U acting a second time. We know that. And here we have the action of a group G. And let's say here we have, again, another action, but of the same group G. The generalization is immediate. So these are two principal bundles for the same group, say. The other thing can be done. And we know, let's just recapitulate what we have. We have U of PG acts must be the same as U of P and the G acts, but with the primed action. That's one thing. And the other thing is that pi twiddle after U is pi. It looks like there's an F missing, but you see if you have a map from M to M, this means this map from M to M is the identity. We go to the same point. This is supposed to commute. So we have these two properties by assumption. And now we need to use this. Aha, how do we do this? U of P1 is U of P2. Aha. So let me see what I thought about what to do there. Aha. Okay. Yeah. So what we do, we look at the pi of the U of P1, and that therefore is the same as the pi of the U of the P2. But we also know that, hang on a second, pi of the U. Okay, I need to take my notes. It's a little bit involved here. Okay, so, I could have also looked at something different. Okay. So we look at the pi of P1. Okay, we can look at this, and then we invoke the first relation here, that pi twiddle of U of pi 1 is the same thing, because pi is pi twiddle after U. But this is because we have assumed that these two are the same is the same as the pi twiddle of the u of the other point, p2. But that, of course, again, is the pi of the p2. So what have we learned? We have learned that if I have this, if I assume that the images are the same, then of the p1 and p2, then the p1 and the p2, they lie in the same fiber. Therefore, pi1, pi2 lie in the same fiber. Aha, but now because they lie in the same, they belong to the same fiber, that means there exists a unique element G in our group that relates the two. So I can say P1 or 2 is P2, or whatever action we want to take. Let's say this one, the primed one, prime G, acts on this. And this uniqueness is due to the fact that we have a free action and that we have a principal bundle, for that matter. Otherwise, this wouldn't be the case. Okay, so this is this thing. And but then you have that U of the P1 is, of course, the U of the P2, and we have this action here on it. But now we refer to this property that's actually the equivariance property of the principal bundle map. This was just the bundle map, but now that we used, but now we use this principal bundle map guy. And the prime is not good. Okay, let's see. If P1 is P2 P prime G, okay, we could have taken, no, the prime is wrong. The prime is simply wrong. There is no prime here because we're firmly P1 and P2 both lie here. The prime is just wrong. Don't need the prime here. We have this, exactly. And then we get U of P2, and then now we have the primed action of the G. But now we know that this is simply U of P1, the primed action of G. Why is that? Well, because U of P1 is U of P2, so we can replace those. And now we see UP1, that means the action of an element G on U of P1 doesn't change the element, right? And because the action is free, since the action is free, it follows that the G must be the identity. Yeah, but if G is the identity, we go back to this point here, and we see, this G all along was the identity, hence P1 equals P2. That's it, okay? And U is injective. And you see we used both the bundle map property and the principal bundle map extra equivariance property. Okay, that's this guy. Now, second, U is surjective. So how did we do that? So we assume let P prime be an element in P prime, okay? And now we need to find a P over here, a little p, such that the U of P is this P prime. Okay, so we again do this in two steps, and we consider first the projection of this guy. We'll see in a second why. So consider, yeah, that's how this works. So consider the projection pi, no. So again, we're looking for a point P in P such that, so look for a P in P such that U of P is the chosen P prime, okay? And consider some P in P such that pi of P has the same, the P has the same base point there as the pi prime of the P prime has. Why can I ask about the same base point? Well, because they both map into the same manifold. And I can certainly find a P in the respective fiber. So if you don't like this such that, you don't know where that exists, I could say choose, that's actually better, choose some P in the fiber over that base point. Okay? So I start with an arbitrary P in P prime in P prime, point P prime. Then I project that point down to the base. And then I look at the fiber over that. And that's different because this is the pi prime. This is a prime, this is a prime. And this is the other pi inverse. I mean, this may have a different fiber structure than this one. So I project down, and then I look at that particular fiber that certainly exists, that certainly is not empty because we have principal G bundles. And I can definitely choose some point in there. So there's no doubt that exists and is not non-empty. So I take this point there. But then I find that pi prime of u of p, let's see what that is. I wrote pi twiddle here. It's a pi prime, of course. So pi prime of u of p is nothing but pi of p. Okay, so I have this. And pi of p, by assumption, is the same as pi prime of p prime. So this assumption goes into here, and this here is the bundle map aspect, not the principal bundle map aspect. We only need the bundle map aspect at this point. So this is certainly the case. And but therefore, it again follows that this guy and this guy, they are mapped to the same base point, because the pi prime maps them to the same base point. That means that the pi prime and the u of p belong to the same fiber. They belong to the same fiber. But if they belong to the same fiber, that means exactly as before, there exists a unique group element G that takes one into the other. Well, it doesn't really matter which one in which one, but that takes u of p by some action of, say, by the primed action. There is a unique G that maps this to the p prime, to the point, to the arbitrary point in the target I had chosen. Okay, but now you can look at this guy here again. So we are talking about a principal bundle map. So we have the u of p acted upon with the primed action by some group element G. That is the u of p where I first act on the p before I map it by the u, but now, of course, by the unprimed action. That's over here. And so we're done. Why are we done? Well, we started with an arbitrary p prime element in here, okay? And we chose some element p that exists. And we know there exists a unique, well, at least there exists some g in G that affects this equation. U of p acting G is p prime. But that means this guy here, built out of a arbitrarily chosen p and a correspondingly chosen g, this is an element in p. So we should say we look for a p twiddle such that this is the case. That is what we do. We look for such a p twiddle, and this guy here, this is precisely the p twiddle we were looking for, because u of p twiddle is the p prime. We're done. Okay, so it's systematic application of the principal bundle and the bundle map property and principal bundle map property here. And so you see, if we couldn't have used this principal bundle extra condition beyond the pure bundle map, neither injectivity nor surjectivity could have been proven. So it's really a strengthening of what a bundle map is on a principal bundle. A principal bundle map is more than a bundle map. It's a stronger notion, and it makes this automatically a diffeomorphism. Okay, so that's a lemma. The question is, why is this interesting? And the answer is interesting because it allows us a very important definition. A principal G bundle well, let's stick for a little to this complete representation of it. Well, that's a principal G bundle. A principal G bundle is called trivial if it is diffeomorphic, so it's trivial, if it is diffeomorphic, but not as a set, not as, well, anyway, not as a smooth manifold here, the P and this, but not only as a bundle, but if it's diffeomorphic as a principal G bundle, so here we could have written in this case the bundle is isomorphic. Anyway, you know how to write this. It's diffeomorphic as a principal G bundle to the following bundle, to M Cartesian product G, which can be made into a smooth manifold, as always. And you have a projection map here, which is defined, I call it pi sub 1, because it just projects out the first factor of this Cartesian product, okay, pi 1, down to M. And I have an action of the group here, so let's call this the solid action. I could call it the primed action, it doesn't matter, it's the solid action of the group here on M cross G, and the action of this group, well, maybe I write it down. So how does this act? Well, you have an element X and you have a G, that's certainly an element in here, and then you act with the solid action on it with some element, arbitrary element G prime. Well, I have several G's here, and this is to be defined as X. The X remains untouched, and you act from also here from the right by G prime, and this blob is the blob in the group. It's very trivial how you act on this, right? And here the pi 1, so for completeness, pi 1 eating an element of the Cartesian product just is defined to project to the first component. So that's the right bundle is defined. You can check this is a principal G bundle. It's a free right action because in the group you always have the inverse. You always know this is the, yeah, that's the unique. It's free. Okay, fine. So you check this immediately. So you have a principal G bundle here, which is the trivial bundle. And you remember at the beginning of this lecture on principal bundles, I said that a principal G bundle very roughly is a bundle with a fiber G. Well, it is a bundle with a fiber G also very precisely, but it's certainly not a trivial bundle like this, right? Here you have a manifold and you attach the group G as a fiber at every point. But that's a very trivial way to make G a fiber, right? If this is a principal G bundle, because of the isomorphism as a bundle to the bundle P down P mod the group G, this becomes also a G fiber bundle, but this is a G fiber bundle in a trivial way. Okay, now the question is, when do you call a bundle, a principal bundle, a trivial bundle? Well, if this is an isomorphism, so if here well, in order to bring it in into the same fashion as the Christmas tree guy here, you have a pi here, and you put the pi 1 here. I could have also written an identity map between the two m's, okay? But I want to compare it to that. If you have a map u that goes from there to there, if there is such a principal bundle map u, if it's diffeomorphic to a principal G bundle, but this is actually set to much because we already have the theorem, we should say it's trivial if there exists, or if there exists a principal bundle map U. Principal bundle map U, like this one. Because if there is such a principal bundle map, it's automatically a diffeomorphism. So we just need to check whether there is a principal bundle map. And again, I emphasize, if we had not introduced the notion of a principal bundle map, one might have been tempted to say a principal G bundle is trivial if there exists a bundle map to the trivial bundle. But that's not enough. We only call it trivial if there exists a principal bundle map, which is a stronger notion. Okay? Principal bundle map. That's this thing. Aha. Good. Good. Now, why are we interested in principal G, in trivial principal G bundles? Well, they're very, very simple. We can think of them globally as having the group just attached as a fiber. Very simple. The question is, how common is that? Is this a strong condition? Is this not so strong a condition? And what does it all have to do with stuff we did before? Okay, we have a little theorem on that. Are there any questions so far? Yeah?
Trivial means that always the same bundle is, the same fiber is attached.
So if you just look at the yellow part of it, well, including this map down here, this is something you would call a trivial bundle because it's made of a Cartesian product. So the right side is a trivial bundle, but you call any bundle that's diffeomorphic to it, because diffeomorphic as a principal bundle, anything that's diffeomorphic to it is essentially the same, but as a principal bundle diffeomorphic. So all the structure here just may look more complicated, but in fact it's diffeomorphic to this. Then any such bundle is called a trivial bundle. If it, after an appropriate diffeomorphism on the total space that preserves all the group action and so on, if it takes this simple form. Okay? That's the idea. And that was the same with bundles before. We said a bundle is a trivial bundle if the total space is the Cartesian product of the base space with a fiber. Okay?
But the fiber remains to be the same for the whole space.
That's right. But okay, so you can say, why is this at all possible? Well, it's at all possible because before we saw, or we rather defined, okay, so let's extend this picture. So the blue one is only due to your question. You have a map from P to P. No, from P to P, that's right. That's another map U. Well, let's call it U twiddle. Another map U. And down here to P mod the G that appears here, mod G, okay, with the corresponding. So that's the orbits or the equivalence, the set of equivalence classes, the quotient space. This is the quotient space map. I don't know how to pi twiddle. And here you have an F twiddle. Okay. We said this being a principal fiber bundle, that's the assumption, this white guy being a principal fiber bundle was actually defined as there being now a bundle map to this bundle. Remember that? There was a bundle map to this bundle where this appears down here. Now, but this, because this G acts by a free action on this guy, so on here sits the free action that we already have. On there sits the free action. Okay, so it should also be blue. They should all be blue. Okay? And because this is a free action, it means that this entire P was, in a sense, foliated into lots of orbits. Okay? But each fiber is isomorphic. We also, I think we mentioned or even proved that is isomorphic. So in our notation of a fiber bundle, this thing is a G fiber bundle. So the blue guy is a G fiber bundle. So this principal bundle is a G fiber bundle, meaning at every point there's the same fiber. Hence, it makes sense in the first place to ask this. This was now going back all the definitions. Yeah.
We just can say that principal fiber bundles are isomorphic to some cross bundle.
Cartesian product. No, not everyone, but if it is, if there exists a principal bundle map U, if from the white guy there exists a principal bundle map U to the yellow guy, where this really should be yellow, right? And this is half white, half yellow. If there exists such a principal bundle map, only then is it trivial. And of course, not every principal G bundle is trivial, otherwise the definition, I would rather formulate this as a lemma, not as a definition for an extra property. Okay? So we saw there are principal bundles that we classify as trivial bundles, and the question is, when is a bundle trivial? And finding a diffeomorphism or finding a principal bundle map, that can be tricky. How do you show it doesn't work or whatnot? So it's good to have a criterion. In this case, it's a sufficient and necessary criterion. We have the theorem. A principal bundle, a principal G bundle, that looks like this, is trivial if and only if there exists a smooth section sigma of the bundle. You recall that a smooth section is a map from the base space back into the total space, for which we have that pi after sigma reproduces the identity on M. That was just what section meant. And the principal bundle is G bundle is trivial if and only if there exists a smooth section. So now before we enter the proof of this, let's invoke something we know. Let's look at the following example. Say M is the two-sphere, and the total space is the frame bundle of the two-sphere. Because the frame bundle is a principal bundle, a GL2 principal bundle, that is P down to M and so on, is a GL2 principal bundle, because every frame bundle is a GL dim M principal bundle, as we saw before today. And now we look at the particular case of a two-sphere. Okay? Now, what do we know about sections of the frame bundle of the two-sphere? What is a section of frame? A section of a frame bundle of the frame bundle would be a frame at every point, right? So a basis of the tangent space at every point. But what do we know about this? Well, there is no such thing, because we don't even have an everywhere non-vanishing vector field. So there exists no everywhere non-vanishing smooth vector field. You remember, you can't comb a sphere, a non-vanishing smooth vector. But if there is not even one non-vanishing smooth vector field, much less are there two linearly independent, separately non-vanishing smooth vector fields. Well, if yeah, well. So that means there is no section. Here there exists, so from this it follows, there exists no smooth section sigma that would assign to every point of the two-sphere a point in the frame bundle. So what do we know about the triviality of the LS2 bundle? Well, it isn't trivial if the theorem applies, because the theorem says a principal G bundle is trivial if and only if there exists a smooth section. Okay? That's it. Okay, so from this again we can see that there are bundles that are non-trivial. There are certainly bundles, principal G bundles that are trivial, namely the yellow guy. Trivially is trivial. Okay, so now we would like to understand this theorem a little better by proving it. So if we first go in this direction, that means we know the bundle is trivial, right? So P, G, P, pi, M, we know it's trivial. Trivial, assume or suppose we have a trivial bundle. That means we do have a bundle map into M cross G that works like this, okay? It doesn't really matter in which direction I go, but let's say I go in this direction. Suppose we have this. If it's trivial, that means there exists such a U which is a principal bundle map. That's the assumption, okay? But then we can construct a section sigma from M to P by virtue of letting sigma of x is defined as, well, I go back here and I take the point x which the section takes, and I simply substitute the identity of the group G over there. Well, if I have such a map, I can always take the identity and push it here. And that's it. And this guy is a section, because if you now apply the sigma here, by virtue of this U being a principal bundle map, it will give you the identity on M. And in here goes that U is a principal bundle map, right? And that's it. That's this direction of the proof. Now the opposite direction of the proof is not that trivial. So now we suppose that a section sigma from M to P, pi after sigma is id M, is given. Well, so assume we have such a section. Then we need to work a little harder. So, so then it follows that for any point P that I choose in the bundle, let me draw a little picture. I mean, pictures are always misleading, but maybe. So the idea is you have the bundle, the whole P, this is the base manifold M. Locally it looks like this. So let's say we have a locally trivial bundle that's like this. And then a section would assign to every point in the manifold a point in the fiber over that base point, which is ensured by this section condition, of course. Okay? So let's assume that this here is defined by the section sigma, locally. It's just to have an idea of this. But now I pick in a fiber, so the sigma be given, and now I say I go to a certain fiber. Well, no, I don't go to a certain fiber. I don't go to any point in the bundle, but that will necessarily lie in some fiber. Okay? And then I have this point P, and I can compare this point P in the fiber. I can compare it with the point I get by first projecting this point P down. So I take this point little p in the fiber, I project it down by pi to here, and then I can look at what the point is that my sigma makes of it. So down here is pi of p, and this here is sigma of pi of p, this point here is sigma of pi of p. I can take this point, and I have another point p in the fiber. They lie in the same fiber, but if they lie in the same fiber, that means there exists a unique, call it G twiddle, in the group, such that the G twiddle acting from the right on here gets you back to the point P. Okay, so now if you talk about this G twiddle, the question is, what determines the G twiddle? Well, certainly it will depend on how you chose which section you have, because if you have another section but the same point here, you need to have another group element bridging the gap, right, by this action. So this G depends on the sigma, but it also depends on the point where you want to go. So it's maybe useful to call this guy chi dependent on sigma and dependent on p. So there is an element in the group which we call chi because it depends on sigma and depends on p, what element that is, but such an element exists in the group such that this equation holds true. It's because of the free action. And the uniqueness is because of the free action. Okay? So, that is, we have a map chi that depends on the given sigma and takes you from P, from any point in P, into the group. Because if sigma is fixed, all you can choose is the point P, and the result is an element in the group. So chi sigma is such a map. Okay? Fine. So we have this. So now we observe that for any G in the group, we can look at this guy and act on it. So we take this equation and we act on it from the right. So we take sigma of pi of p, a right action, chi sigma of p, and for good measure we act again on the right with an arbitrary group element. We can do this, and although it can't be read in any other way, for our comfort, let's put brackets here. And, well, that's the left-hand side. Well, then obviously this must be true, because the bracket is P, so that is P acted upon from the right by a G. So now, however, we know that this is a right action. And because this is a right action, we know that this left-hand side is sigma of pi of P acted upon by this group element geblobbed with this group element. This is simply by virtue of the triangle here being a right action. Okay, and now this right-hand side, however, the G acts on there. I can of course rewrite this as sigma of pi. Hang on a second. Sigma of pi, no, that's not true. What did I do here? Hang on. So this is certainly true. Aha. So this is this, but because this is this, I can also, okay, so let me write down this left-hand side in yet another, but hang on, can that be the thing I want to do? I'm sorry. I want to get the G out. So what I want to show, is that X sigma applied after I act on the P is the same as chi sigma P and then geblobbed with the G. Okay. So I have this. Now, certainly from up here, since the action is free. How do I get this guy? So I want to rewrite this right-hand side. Now this P is this guy. So let me just repeat this, but then modify it, of P, and on it acts a chi sigma of P, and on this acts a G. That's just a rewriting of this side, okay? We did this before, and it goes to this, but this guy can also be written differently. What happens if I have a P, and I act on the P by a G? Well, nothing happens because I remain in the same fiber. That means the pi doesn't change a thing. Okay. So that's certainly one thing that's true. And okay, so you want to insert here a right action by the G. That means there's a right action by the G here, and there's a right action by the G here. That's what you're saying.
Yeah, on the right side.
And, yeah, of course. And then on the right as well. Yeah, that's right, exactly. And that is what I want here. So I get exactly this, and then I get the P and the action of the G on it. And that is, of course, this guy. Yeah, that's right. Oh, thank you. Okay, so sometimes in front of the blackboard. Okay, right, so we use this, we use that. Okay. But now we have this, but this guy here can be, again, sigma of P of pi, because we remain in the same fiber, so we stay at the same base point. So that means in total, we know that this guy here equals, because we go via this equal sign, equals this guy here. Okay, agree? Okay, so let me write it down again. So this means that sigma of pi of P acted upon by X sigma of P blob G is the same as sigma of pi of P acted upon by chi sigma P acted upon from the right by G. Now, this here is just a point in P, in capital P. This is the same point. And we have an action of a group element on it, and the action of another group element on it, and it acts on the same point, and the result is the same. Now, because the action is free, this can only mean that the two group elements are the same. So because this action is free, yeah, thank you, that was, yeah, I didn't see it. Just use the definition again. That means that the group element chi sigma of P blob G ought to be chi sigma of P action of G on the right, and this is what I wanted to show. Okay, good, good. So this is something we needed. Okay. Now, once we have that, So now we're in a position, starting with this section, we're in a position to define. Now we can define, we can start from our principal bundle. And we can define a map U that depends on the given section sigma, because in this direction the section is given. And we can construct a U to over here, right? Such that the U is a bundle map, because once we have that, we have established that the whole thing is trivial. And we define the U sigma from P to mg, m cross G, as the map that takes a point P to, well, where can it take it? It can take it to the projection of the point P, and we have a map psi that takes us from P to the group. Well, we'll simply invoke the just constructed map with that property we'll need in a second here, and this will certainly be an element of M Cartesian product G. So we defined a map from this set to this set. The only question is this a bundle map? And if it's a bundle map, is it a principal bundle map? Okay, so we constructed such a thing still to show U sigma is a principal bundle map. Because if it is, according to our little lemma, we established already the diffeomorphism, we established this is a trivial bundle. Okay? So is this a principal bundle map? So let's first check whether it's a bundle map. A bundle map, we need to check that the pi 1 here, so we need to check that pi 1 after this U sigma is the same effect as the pi. You remember? Down here the stuff, that's the bundle map business. Okay? But this is obvious because the pi 1, I first apply the sigma, and then the pi 1, it projects out just this part, but that's of course the action of the pi. It's trivial. That's like this. And in order to show that it's a principal bundle map indeed, we need to consider what happens if our U sigma acts on a P and how that relates to the action with the G, because we know if it's a principal bundle map, then that must commute in a sense. You know, we must be able to pull the G out here. And so we have another action here. I think we called it the solid action of the same group, M cross G. And what we need to prove at the end of the day is that all of this is U sigma of P and then the solid action of G on it, right? This is then the compatibility up here because U sigma is here. This is the bundle map business. This is the principal bundle map business, okay? So we have this, and so that means we simply calculate this. And so what is this? Well, by definition, U sigma of P acted upon by G is pi of P acted upon by G, comma, x sigma of P acted upon by G. This equals, here we stay in the same fiber because we have a free action and principal bundle, This is a pi of P. And now you see why we had to show that if you act first on the P and then you employ the chi sigma, that you can actually also first employ the chi sigma and then blob this with the G. This is why I had to show this before. That is exactly what happens here. So you have a chi sigma of P and it's blobbed with the G. But if you remember correctly, this blobbing here we're of course we're in this bundle. There the solid action works, and the solid action, we acted on elements in here from the right by just blobbing the second element of this Cartesian product with the G. Right? That was the definition we did before in this trivial bundle. And so this is pi of p, comma, chi sigma of p, and coming from the right with the solid action. Aha, but this is precisely what we wanted to show, because pi of p, chi sigma of p is precisely u sigma of p. So indeed, this u that we constructed from this chi sigma, which in turn was constructed from the action and has this property, which is easily proven once you look at it carefully. Thank you again for the help. This makes this u sigma a bundle map, but even a principal bundle map. Hence, we're done, because once you establish that a principal bundle has a bundle map into the trivial bundle, then this principal bundle is trivial. So having a section means the bundle is trivial, and the other way around, if the bundle is trivial, you can construct a section. Okay. So we now confirmed that what we did before, that we used our theorem in establishing whether the principal GL2 bundle provided by the frame bundle of S2, whether this is trivial. No, it's not trivial, because there is no section of that principal bundle. And in previous lectures, we related this to there being no basis for vector fields in the module, and the module of the vector fields, the C infinity M module that constitutes the vector fields, not having a basis, meaning it's not a free module, it's just a projective module. You remember that was the Serre-Swan theorem. Okay, so all of these things belong together, and this theorem is a very important result. Okay, questions? Okay, so then see you after Christmas, and we'll continue with associated bundles, and then you'll finally understand why we're so interested in principal bundles, because they have associated bundles, and in the associated bundles live the objects we like so much. Spinors, tensors, tensor densities, and all of them are the principal GL4 bundle, for instance, thrones over them, or the reduced SO13 bundle thrones over these other bundles. And that is, if in physics we say we rotate something, we do an SO3 transformation, how do all the different objects, which are all sections of different associated bundles, transform under the same transformation which we understand in terms of the principal bundle. In this sense, the principal bundle really thrones over all of the others. If you understand the principal bundle, you understand all the associated bundles. And that's the idea. Okay, see you after Christmas.